Hello, Niranjan.
Good morning, Dr. Sajas.
Hi. Okay. How did the homework 6 go? Are you guys? No. Homework 6 was due on Friday, right? And then it was postponed, I suppose, or today. Yeah, today. So how have you guys tried it out or still waiting? Okay. Anything special about it? Okay. Questions? Homework 7 will be due Monday. This will be probably 9 plus 7. 15. Is that? Yes. Yeah. I hope I didn't make a mistake in the undergraduate. Monday. So there was a suggestion made that I will make I made a bonus question just in the fly. So I was teaching and then I asked you guys to submit. When I looked at it, I feel unless it helps everyone, I wouldn't like to use that. And it turned out that at least one of you guys get hurt with that. So that bonus question is not really a bonus question. Okay, so I withdraw a statement. Is that clear what I said? So it doesn't account for your exam. I'll try other ways to help the class as a whole. That particular question was affecting people, like at least one person affecting. So let me not use that. So, okay. So bonus question has been cancelled. And there was a question asked as to whether your grades are significantly low, that your A's are, you don't have a chance for an A or not. I curve a lot, so don't assume that at this stage. So you should all work hard. As far as I feel everything is like there is a lot of curve that happens in this course. So keep working hard. Don't give up, including an A. That was a question. Yes. Okay. Any other general questions? Okay. So we want to do what is an analytic function. And specifically, analytic function is that in the context, you define something called an analytic function, both in the context of real and complex variable. They're different. So we are talking about analytic function of a complex variable. In simple terms, we are talking about derivative. When we have a real function, which is depending on a real variable, then you define what are the how do you define a derivative. Similarly, we would like to define the idea of a derivative of a complex variable, and it will turn out that since it is on a two-dimensional surface, there will be conditions that will impose on it, and those conditions geometrically put in a lot of constraints on what can be an analytic function, and that will be our idea. And it's a very powerful concept, and it allows, and there are various applications associated with it. One of the applications will be contour integrals, and we will work on that in the next class, presumably. Okay, let's go back to real function. So digression, so real function. So we are saying, let's say f of x. Often we use the variable x for real and z for complex. So x and y, let's say. So z will be equal to x plus I and y. Like it is sort of, it is not necessary that every time I use x, it is real, but more often, without even defining, I'm saying that x is real, y is real, and z is complex. So complex number is built out of two real variables. So you can imagine a complex number as a function on a plane. That's how that's a standard way of looking at it. So a real function is a function on a real line, one line, and a complex function will be, the domain of the complex function will be a region in a plane. Right? So that's but let's restrict ourselves to real function. How do we find the derivative? So the f by the x, how do you define that? Suppose you go very back at a very basic level, at a very fundamental level, the first step. How do you define, if I'm given a function, how do you define the derivative? Arbitrary function, anyone? Yeah, so that's how I think that is this. Yeah, that's how the Newton defined it. So you say that, okay, I want to change the functions in a finite manner. So x plus delta x. So here delta x usually means not infinitesimal. Is it I-E, right? No, is it I or E? I think it's E, right? I, right? Spelling? Okay. I think it's I. And dx somehow, this is not even, yeah, delta x not infinitesimal, that is sufficient. And dx is somehow in the limit delta x, it becomes dx, but then you don't separate that dx. Okay, so that's a not necessarily infinitesimal, but if I take a limit, it can become. So this will be a change in f, right? So a change in f will be f of x plus delta x minus f of x. So if I were to have a picture for this. So I have a function. Since it's a real variable, I can use one of the coordinates for x and the other coordinates for f of x. And E. It is E. Okay. Oh, and then there is one more. Infinitesimal. Still. Okay. I was always doing it wrong. Yeah. So that's your real variable x. Since I'm in a one-dimensional function, that is only real variable, I have the luxury of using the other axis as a function. Define your favorite function. Let's take a simple function. I'm interested in the derivative at this point. Let's call it x, even though I'm using that as a value. And this point here is x plus delta x. Switch this a little bit, so all of us have seen this, but reminding doesn't hurt. And even though I'm interested in the derivative at position x, I go for the next point, right? So not necessarily the very next, I go a finite. So this is f of x, and that's f of x plus delta x. And this difference is delta f. And this difference here is delta x. That sort of gives you a triangle here, which is how we look at it. So that's delta f, that's delta x, like this. That's Newton's idea. But, and he will use the word, so he didn't use delta x. Instead, he used O, right? Small letter O for that. And that was a notation that no one liked. And because it is taking a limit 0, that's why he used the letter O, but I think no one liked that notation, or it was not a very popular notation. Okay, so the same thing here without the function x plus delta x minus of x. That's it. Derivative, of course, x cancels out, and that is delta x. And you want to take the limit, delta x tends to 0. That's the definition. You cannot do much unless you have a way of writing your function in terms of delta x. And that is what, again, going back to Newton, I mean, Newton is the one who wrote it in this manner. And he was very good at series expansions, right? He's the one who started the binomial, he's the one who gave us the binomial expansions. So he expanded this for our purposes. Let's say that every function has a series. It has a unique series representation. And by series representation, I mean, if you think of a function f, right here, right, the function f of x, every function you can think of as f of x. If I'm evaluating at a point, so let's say this is 0. If I'm evaluating at, let's say, how do I put this? Let me write this as f of x plus a. That's some value of the function. If I'm interested in the value of this, so I'll say it is f of a plus x times d by dx of f of x evaluated at x of a. And I made a mistake, I suppose. No, this is okay, right? Delta x or this is x plus a. I just wrote it as. I'm just doing it. I'm just giving you a series expansion. Isn't it correct? Second one. Delta x or derivative of the x. Okay. This one? No, this is x, right? It will be x plus a minus of a. Isn't it? Okay, how about this? Okay, we'll do this way. Sometimes I like to do this f of x, right? You're evaluating at the point x plus a d by dx of f of x plus a squared over 2 factorial times second derivative of f of x and so on. Now notice we are defining the derivative, so you cannot use the idea of derivative here itself, right? So usually how you say this is that you can always expand this x. You're expanding it in a, so it is f of x, so let's say a0 alpha 0 plus a times alpha 1 plus a squared over 2 factorial by times alpha 2 plus so on. But alpha 1, alpha 2, alpha 0, alpha 1, alpha 2 are numbers. Alpha 0, alpha 1, alpha 2, and so on define the function. For example, let's do example since there was some confusion. Let's say example. Exponential of x. Again, do x plus a instead of exponential of x. Immediately do. So I'm interested in, let's say, f of x is equal to exponential of x. Instead, I do f of x plus a. Idea is to make a small, but if I do x plus a and then I expand it out, and how much will this be? This will be equal to, we know the series expansion, so it is 1 plus x plus a over 1 factorial plus x plus a the whole square over 2 factorial and so on. But you have to collect all the powers of a and a square and so on. So it is 1 plus x squared over 2 factorial. So there is some work needed in this. So this is all one piece. And then there is a. And you say it is 1 plus a. 1 plus 1 over 1 factorial plus so on. So that is yeah, 1 plus no 0 plus 1 plus 1 factorial a, so it is plus 2 times a times x over 2 factorial and so on. 2a and so on. And you will see that this is nothing but exponential of x itself plus a times exponential of x plus it will come out that is squared over 2 factorial times exponential of x. So in this case, alpha 0 is equal to e raised to x, alpha 1 is equal to e raised to x, and so on. What I mean to say is that if you have a series of a function that completely defines it, like maybe in this way of writing it, it was not very useful. Even at this stage, I can say, right, 1 plus 1 over 1 factorial times x plus 1 over 2 factorial times x squared plus so on. These coefficients, 1 over 2 factorial, 1 over 3 factorial, that defines your exponential. There is no other function which will have the same coefficients. The coefficients decide the function. Like if they come in opposite order and let's say all the odd terms are 0 and even terms are the same, what is it? What is the function equal to? If all the odd terms are 0 and the even terms are the same, cosine of x, right? So that's a unique representation of it. So this is 1 plus 1 by, it is, yeah, is it correct? Yeah, right. Plus x raised to 4. There is no sign thing, right? Okay. My whole point I'm trying to make is that if you have a series, then the function is unique. So we use, so whenever we say this is a function, I'm going to expand that out now, but now in terms of delta x, that's why I was writing that in that form. So that's delta x tends to 0. And now notice f of x, that representation is useful here, plus delta x times, in this case, let us call it alpha 1. So this is delta x over 1 factorial times alpha 1 plus delta x squared over 2 factorial times alpha 2 and plus so on, minus of f of x. Divided by delta x. it is crucial that this f of x cancel out. And if that cancels out, there is a very simple but profound interpretation here, that we have delta x times alpha 1 plus delta x squared over 2 factorial alpha 2 plus so on divided by delta x. This is the same as alpha 1 plus delta x over 2 factorial alpha 2 plus so on. And this tells me that this is alpha 1. So the derivative is the first term in the series expansion. So my question is, how good an approximation is this? We are actually neglecting this, correct? How good an approximation is this? So I use the word we are neglecting this. Is that a true statement?
Depends on delta x.
But delta x is tending to 0. It's truly in the limit. This is not really an approximation. Okay, in the true limit, that's what the limit means, that there is no, we don't stop, right? We don't say it is 0.01 or 0.01. Of course, we imagine that it is 0.01, 0.01. But this is infinitely tiny. Since this is infinitely tiny, this is 0. Unless this is 1 over 0. By any chance, this comes out to be 1 over 0, then you're in trouble. But if this is finite, like by finite, I mean it's not 0. It's not, if it is, let's say 56, or even if it's 1,000,000, I can always go delta x small, that it will beat it. And this is an exact statement. It's not an approximation. That's what I'm trying to say. In that sense, when I take this delta x tends to 0, the derivative is really the property of that point, even though we define it as a property of the difference between 2 points. When I take the limit, it really goes to 1 point. But of course, it needs the neighborhood, but it is the property of that particular point, in the sense that it's not really dependent on distance. So that's the simple idea of derivative, but really change our perception of a function, change the development of analytic calculation altogether. We want to do this for 2 dimensions. So before I go into complex numbers, so let me first do this for 2 variables. I can always do this for f of x comma y, right? So still I'm having real function. So I have f this time of 2 variables. So 2 real variables. And now we should again think of what do we mean by derivative? And if you are on a plane, how will you define a derivative? Yeah. No, yeah.
Like a slope.
Like a slope, yeah, but what is a slope?
Surface.
So we basically, yes, we are having, what we are having is there is an x and a y, right? And f is real, okay? This is also real, let's say. So you can think of a shape on the xy plane, think of a Gaussian shape. This is a mountain on a valley. So you have x and y to be your terrain, and there is a mountain, the height of the mountain tells you what is the value of the function. So my question is, how do I define the derivative of this function? Like, let's go with this idea, but how would you define that? Like, numerator probably is f of x plus delta x. So I go from one point. So that's your x, and that's your y. And I go to another point, right? So I have to pick another point. So I have to do an x plus delta x. But notice I choose, right? I can pick any point close by. So there are lots of points I can pick. This is x plus delta x and y plus delta y. So there is a whole set of points I can pick around here, not necessarily around a circle, but at least in the neighborhood, I can use, I can find a lot of points around that. And you would say that our change in f will be totally this. Minus of f of xy. Okay. And then divide by, what will you divide it with?
I do the same thing, x plus delta x minus x.
So the distance.
And also y.
So you would say this distance is, let's say, r. So you would say it is x plus delta x minus x square plus y plus delta y minus y square. Is that the solution? Which is nothing but delta x square plus delta y square. Little bit. Yes, that means, yeah. Is that the solution?
X plus.
Huh?
Delta x plus delta y.
Here you say just delta x plus delta y. Yeah, sure.
Multiply the two, just x plus delta x minus x. Multiplied by.
So the solution is x plus delta x multiplied by y plus delta y. Like, so my question is, what's in the denominator, right? So maybe it's equal to this. And the solution was delta x plus delta y. Let's take a simple one. Let's take delta x plus delta y. It's wrong. I mean, there's nothing wrong in it. This is a matter of definition, correct? How far can you proceed with it? Is it a useful definition or not? That's the point. I mean, you can define any small distance here. And the point is that, can you define something so unique in the end? Like, this is very unique. If you take the limit, this always comes up for a given function. This will always give you that value. And the question is, can we define such a quantity? And it turns out it is not possible to be unique in the way you approach. So it depends on in what direction you approach. Here, the problem is that if you approach in this direction, there is one derivative you get. If you approach it in this direction, you get another derivative. And that's not a very useful idea, because then you have to say, oh, in what direction I'm coming in from. Right? So it's a direction. So in 2 dimensions, the gradient that you define, this is nothing but the idea of a gradient we are building, right? Gradient, if you remember, gradient is I hat d by dx plus j hat d by dy. Gradient is a directional quantity. It depends on in which direction I'm going in. So it turns out that you can define it in that manner. So let's take delta x plus delta y, again, one should be careful. This is not the correct way of defining the gradient. But if you were to do this, this will come out. Let's say this is whatever, let's call it D. Okay, whatever that means. And what I would like to invoke is that what is this now? Like, you know, the series expansion of a single variable. What's the series expansion of double variable? You expand it in one variable, pretending that the other one is fixed. And then each term in the second variable expand the second one. For example, let's say, so let me do it here. Right? So f of x, y. So let's fix that. So f of x, let's have a and y plus b, right? The same thing, delta x and delta y. First pretend f of y plus b is just fixed. So this is f of x, comma y plus b, plus a times derivative. This time I write partial derivative. So we'll put it in there. So this is f of x, comma y plus b. I just write y plus b is just a spectator there. I'm not doing anything to it. Plus a square over 2 factorial, and I'll do d square by dx square times f of x, comma y plus b. And that's how you will proceed with the derivative, but I can expand this also now. Like each of this y plus b I can expand, and that's equal to f of x, comma y. So this is the first term alone, plus b times derivative with respect to y of f of x, comma y. Here the understanding is that the derivative of y, it's only on the second variable, right? So this is, I'm expanding this alone. I'm doing only this now. I'm not reached there. So this is b squared over 2 factorial, second derivative with respect to y squared of f of x, comma y, and I keep going. This is all for the first term, right? First term, I'm pretending that now x is fixed and I'm expanding y. I'm using single variable expansion twice. So now there is more to this. So now I have to do this, right? I have to expand this. So this will be a times d by dx of f of x, comma y. Plus expand this again. So now I get a times b of d by dx and d by dy of f of x, comma y. But as I'm doing this now, right? So this is all. So this line is all double line. This is triple line, right? This is a. Is that clear what I'm doing? So this is being expanded out. This is being expanded out, and next I will expand this in the third line. This is plus a b squared over 2 factorial d by dx times b squared by dy squared times f of x, comma y. And finally, plus a squared over 2 factorial, second derivative with respect to x squared, plus there's a e now, so there's a squared d over 2 factorial d by dx, d squared by dx squared, dy. And finally, b squared, d squared. And that's here 4, right? 1, 2, 3, 4. Is that clear how I proceeded with that expansion? At that stage, so notice what we do here is that it's usually the first order term that contributes. Okay, unless this is also playing an important role, which happens often in physics, that we have to go to the second order term also, that's very common. But in the derivative part, it is usually the leading order that gives you the derivative. So if we decide that we are going to keep only the leading term, then first let's take only the two, right? Suppose I agree that only 2 second order is going to be kept. That's going to be kept. All this is lower. This is second order. This is third order. So I don't keep this higher orders, right? Fourth order. And this is third order. This cross terms means higher orders. I'm not really neglecting it. The way I have done it, it seems like I'm neglecting it. I'm supposed to do this. I have to bring it all the way till here and then take the limit and take it to 0. So I don't want to drop it here, but I'm trying to highlight that these are higher orders. So I'm not really going to drop it. There's no approximation when you're defining a derivative. Okay. So if I were to do this, f of xy will cancel out. So because f of xy cancels out, so derivative of this function will be, so I have the leading terms will be b. So let me write this as a times derivative d by dx of f. So I'm not writing the x, let me write x comma y plus b times derivative d by dy f of x comma y plus higher orders. Oh, when I say this derivative, this is delta x. This is now delta x plus delta y. And I should also give this a name, right? Sorry. Change the class. So this is alpha 0, 0. This is alpha 0, 1. That's alpha 1, 0. And this will be alpha 1, 1, and so on. So what I have here is delta x times alpha 0, 1 plus delta y times alpha 1, 0. If I keep higher orders, this is delta x, delta y. If this is leading order, that's the second leading order. So this is alpha 1, 1. But rest everything is more than that. Oh, this is also there, x squared. So this is delta x squared. Delta x squared is here plus alpha 2, 0 plus delta y squared times alpha 0 cube plus higher orders divided by delta x plus delta y. Remember, you don't want to do delta x plus delta y, but we just took an example of what this could be. I'm going to say that this is not really easy to work with. The limit of delta x tends to 0, delta y tends to 0. If I were to have the alpha 0, 1 equal to alpha 1, 0, these two cancel out. This doesn't this cancellation was important here. Right? Only when delta x cancels out, I have a well-defined quantity. Here, what I'm getting is, if I were to do this, I get delta x. So the limiting expression here is delta x over delta x plus delta y times alpha 0, 1 plus delta y over delta x plus delta y alpha 1, 0, and all this will go to 0 because these are higher order. Well, there is 2 zeros here. There's only 1 0 in the denominator. Plus, you can take the limit 0. But this is not well defined. That's the derivative of the function. If you were to define it, whatever you do, unless delta x and delta y are related, if you come along a line where delta x and delta y are related, only then you can be very good about saying that this is unique. It depends on alpha 0, 1, and it depends on this ratio. This might not be like this is not undefined in a sense, but it's not unique. It depends on what direction you come in. For example, if you're coming in along 45 degrees, then delta x and delta y is 1. Right? So 45 degrees implies that delta x is equal to delta y. And then it is 1/2. But if you come along the x-axis, delta y is 0, so that is 1. So the derivative depends on in what direction you come from. So that's the challenge with 2 dimensions. Okay? And you don't get away with it. You only say that there is a gradient operator which is directional derivative. It has a direction associated with it. Gradient is always, the way you say it is that A dotted with the gradient, right? So you say this is gradient in the direction of A. That's the way you define it, gradient. But in complex analysis, we are going to have a nice way of defining this, or there is at least one definition of a derivative, which will not have this feature. You will be able to come in any direction you want, and it will always give you the same number. So that's what we are going to, or we are going to impose that. We might be able to do that here also, but in complex analysis, that really comes out nice. Okay, any questions at this stage? This is all review in a sense. Okay, so we come to a complex variable now. By complex variable, we mean f of z. That means f to z is equal to x plus I times y. X and y are real, and now f itself is a complex number, so it is u plus I times v. X, y is real, u, v all are real. Z and f are complex. More explicitly, what this means is that I can write this as u of x comma y plus I times v, which is a function of x comma y. So now we are suddenly not having enough access to represent this. If I have to define a complex function or a function of a complex variable, I have x comma y. That's my domain. Right? That's my domain. But the range is also complex, so there are 2 variables. So I cannot use a single axis to represent this. Now here I can say that the z-axis I can use for my a function, but z alone is not sufficient. I need a u and a v. So you go from a plane to a plane. So that's u, that's v, and that's your function, and that's your range. So the function goes from this to this. So this is your function of z. How you show that is that, so suppose you have a point z here, that's your z, that will be, it doesn't have to come into the first quadrant, so it could be f of z might be here. Typically, we are interested in few points. So if I were to pick a z prime, z prime is somewhere here. I go this direction, that's z prime. F of z prime might go very far away, so it doesn't have to be going here at all. This might be somewhere here, f of z prime. So idea is that go there. So there is a connection So there is a mapping from every point on the plane to every point on another plane. That's a complex function. Two variables, x and y, two variables u and v. For a given x and y, which is a complex number, there is a u and there is a v, and that's represented by a point in a new plane. Right? That's how you want to visualize it. So it becomes very hard. So suddenly you're in a four-dimensional feature, and that's what makes the geometry of a complex function slightly hard. We want to define a derivative. So this is how we will define a derivative. Right? The f by dz. This will be equal to limit. Again, we have the same problem. Remember that one might say that, oh, this is directional, right? We are in a plane. I can approach z in various directions, and we will remove that directionality by putting some constraint on it, and that's what we will call an analytic function. So we'll say that delta z tends to 0. What do I mean by delta z tends to 0? I mean the magnitude going to 0. So in the true sense that both x and y have to go to 0, right? In this way of saying it, but I have to make it more concrete. Because it's the denominator. So this will be f of z plus delta z minus of f of z divided by z plus delta z minus of z. And what is delta z here? One might wonder what delta z is. Delta z here, where delta z, because that's what we struggled with right here, right? How is it a distance? Is it a delta x plus delta y? I mean, in principle, when you define a gradient, it's defined as a vector. Delta z here will be defined as a complex number, is delta x plus I delta y. So give me any x and y that is close to, so this is my z, so that's my x, that's my y, and that's x plus delta x, same thing that we did there, but this time I've made it more precise, a little more precise. Still, it is expected that it will be directional, but we will remove that condition in a few minutes. And if here the when I was asking the question, oh, what should I define with? I was hoping that there will be a vector. Someone will say that, oh, you define and divide it by a vector. And the challenge there is that vectors you don't divide, right? You don't divide by a vector, and probably that's why you guys did not answer the question. That's what makes it difficult in 2 dimensions. You don't have division very well defined in 2 dimensions. In vectors, you cannot do that. But in complex numbers, division is defined. So if division is defined, that means you can do this in a concrete way, right? The division is very well defined. Remember again, so when I say this 1 over delta z means that 1 over delta x plus I delta y. How do I do division? I can make this a square, so I know division by a real number. So I can make that a division by a real number, which connects with the suggestion there, right? This is a squared quantity divided by delta x minus I delta y. That's equal to the complex, the delta z star divided by, this is the magnitude of delta z. This is, maybe I should write one more step, delta x minus I delta y divided by, this is delta x squared plus delta y squared, which is one of the suggestions you made in 2 dimensions, right? So this is delta z star times delta z magnitude squared. Right? Delta Z times delta Z star if you want, right? That's a magnitude, and that's a real number in the denominator. It's a real number, and we know how to divide by a real number. So division by a complex number is well defined by multiplying, which usually is well defined, and dividing out by a real number. So let's do this in the concrete way, just explicitly. Just let's evaluate this and see what happens. So derivative of a complex function is defined as, you have to expand this. Now notice this is u, right? So this is u of x limit. So I have limit. When delta z tends to 0, I'm basically saying delta x tends to 0 and delta y tends to 0. That's delta z tends to 0. So this is u of x plus delta x, y plus delta y, plus I times v of x plus delta x, y plus the y minus of u of x, y minus of v of x, y. Divide by, let me write this as delta x plus I delta y. Here I was basically demonstrating that delta z is well defined because I know how to divide by a real number. Right? In that sense, it is. We know how to expand a two-variable function. That's what we explored just a few minutes back. So let's expand this out. Equal to limit delta x tends to 0, delta y tends to 0. The first term we know will cancel out. So the second term will be delta x times derivative of u with respect to x. There will be one more term here, delta y times derivative of u with respect to y. That's the first term, plus I times delta x times derivative of v with respect to x, plus derivative of v with respect to y. I subtracted out that u and v, right? I series expanded it. And if you want, there are higher terms, right? Plus higher order in delta x and delta y. Divide it out. Any questions here? Because I wrote this in a single step because two variable Taylor expansion I already defined in the earlier discussion. Let me collect this delta x and delta y so that I can see this expression better. This is delta x, delta y times 0. So I have delta x. I collect these two terms together. I'm changing the organization of the terms, plus I v x plus delta y higher order is often written as delta x, delta y, right? And you want all the second order terms are cancelled. Second order terms are I wouldn't say can, I keep saying it wrongly, like I'm not neglecting it. So I want to keep that, but the limit they want contribute. Divide it out by delta x plus I delta y. Do a small manipulation here just so that it looks kind of the same thing. I put in an I here, and then I put in a minus I inside. So there's an I here. That's minus I. So minus I and an I, that becomes a plus. That's the same thing. I just manipulated that a little bit. So I put in an I, or I pulled out an I. This has the same problem. This is not the same. So they don't cancel out. Delta x plus I delta y does not cancel out. The same problem has the derivative in 2 dimensions. We have the same issue. But here we are defining. There I was arguing that if you come along a line, right? If you come along a line, delta x is equal to delta y. If that was the case, if delta x was equal to delta y, then I have the cancellation there. Can I do the same thing here? And yes, here, this is what we will put as a condition. So what is an analytic function? We will say that these two are the same. Okay, so what is an analytic? So now it's a condition, right? So until here, this was just algebra, but now constraint or definition of analytic function. Or this is how you make it a directionally independent derivative. Direction independent derivative. And the idea is to make this the same. If I make this the same, so these are called Cauchy-Riemann conditions. Cauchy-Riemann condition. This is one property that changes complex analysis completely. That is that this is the same as this. So you say du by dx plus I times dv by dx is equal to minus I du by dy plus d by dy. If that is the case, if this is true, then delta x and delta y cancel out. Then derivative of the f by dx dz. Now I can take the limit. Everything goes through. There is a limiting process. The well-defined limiting process. And since this is the same, this is either equal to du by dx plus I dv by dx, or it is also equal to that. Right? So it is this this plus that, so it is 2 times that, right? So I cancel that out, so it is 2 times. Or it is also equal to 2 times minus I du by dy plus dv by y. So that's going to be your derivative, and I've taken this allows you to take the limit in a unique manner and give you a unique answer, and that's the unique answer. Because if these two are the same, that's 2 times that. Either you say it is this, or you say that is that. I can also rewrite this in a minute. I will do that, but let's explore this a little bit more. Okay, the Cauchy-Riemann conditions. Let's explore that. Again, f of x, y, or f of z is u of x, comma, y, or I times v of x, comma, y. Often you stop writing your x and y, that's understood. That is u plus iv. Z is x plus iy. One plane to another plane, right? Domain is a complex plane. Range is also a complex plane. Now, Cauchy-Riemann conditions are analytic function. The definition of an analytic function is du by dx plus dv by dx is equal to minus I u by dy.
Why do we need the two here?
Me? Yeah. Isn't this correct? Okay. So I pull this out. No, that's not true, right? Yeah, that's not true. Okay, let me see. Delta x plus a plus I times delta y plus b, let's say. Yeah, if a is equal to b, yeah. You're right. Okay, so that's equal to, if a is equal to b, if a is equal to b, then I just take a delta x plus I delta y divided by delta x plus I delta y. That's equal to a. So either a or b might. Yeah. So there is no q there. Okay. I wrote that wrong here. There is no factor of 2 there. Okay. Did everyone register that? Check that. So there was a factor of 2 there. My bad. Okay. So this is Cauchy-Riemann condition, but these are complex numbers, right? Complex numbers. If two complex numbers are the same, real part has to be the same, imaginary part has to be the same. So Cauchy-Riemann conditions are two conditions where du by dx is equal to, so the real part is dv by dy. That's the first condition. And the second condition is the imaginary part, dv by dx has to equal to minus of du by dy. If these conditions are not satisfied, it cannot be analytic. Okay, so then you cannot define a derivative. So derivative, if you want to define the derivative of a function, not every function has a derivative to begin with in complex functions. So the first thing you have to ask is, if someone asks you, oh, give me the derivative of a complex function, you first ask, does this even have a derivative? And those functions that have a derivative is what is called a analytic function. So analytic function satisfies the Cauchy-Riemann condition. So let's do a simple example, correct? So let's say f of z is equal to z squared. That's one of the simplest function you can build, right? By multiplying two numbers. So what is your u and v? So I have to first identify my u and v. So I say this is x plus I y squared. That's equal to x squared minus y squared and 2i xy. So I immediately have u is x squared minus y squared and v is 2xy. Check if these derivatives are true or not. So let's do du by dx. Du by dx is 2 times x. Let's do du by dy. I'm just going to collect things here. Du by dy is minus 2 times y. Taking this and taking the derivative. Dv by dx. Dv by dx is dv by dx is 2 times y. And dv by dy is 2 times x. And now we want to check if this is satisfied. Derivative with respect to x has to be equal to derivative with respect to y, right? These two have to be the same. And that is indeed the same. and du by dy has to be the opposite, right? So this is anti. You want these two should be negative of each other, and which is indeed the case, right? However you do it, doesn't matter how you check that. So this satisfies the Cauchy-Riemann conditions. That means that at least there is a hope. It doesn't mean that every function that satisfies Cauchy-Riemann condition will have a unique, it is analytic. We will see that this is only a necessary condition, but not a sufficient condition. So sometimes even if it satisfies this condition, even then it may not have a derivative. That typically has to deal with infinities. Remember this differentiation requires that this is not infinity, right? If this is an infinity, then you can multiply a zero and spoil everything. So if this has a pole, then you are improper. So this is the basic input you can pick in. Should I say at this point? Yeah, maybe. Yeah, few quizzes. Couple of quizzes. And so quiz. I try to explore this condition. It is hard to visualize, very hard to visualize this. Try to visualize this and try to give me an answer as to, is there a function? Can you give me an example of a function which is analytic everywhere? Okay. So give an example of a function. By that we mean a complex function which is analytic everywhere. Remember, analytic now means that it has a derivative. Right? We would like to think of a function which has a derivative at every point. In real functions, give me an example of a real function which has a derivative everywhere. At every point on x. So in real function, it is this is usually easy to visualize f(x). At every point on x, irrespective of where I am, give me an example of a function where it is a very good derivative exists. Any function, even it's like sine x squared is an example, right? X squared as a function, sine of x. You can think of a derivative at every point, right? So there are so many functions available. Give me the same in complex function. Think of a function which is analytic in a complex any function. So there is a pattern. What my point is that there is a pattern that you look for where you say that, oh, this must be analytic, at least in a preliminary state. The second is, so this is quiz 1, quiz 2. So if you have a function of z is equal to u of x y plus I times v of x y. When we think of this, it seems a little off in the sense that there is a z is a function of x comma y, right? So there are two variables, but here there is only one variable z in the sense if I think of it as a variable alone. So you can think of z is equal to x plus iy and z star as x minus iy. So think of functions which are functions of z star. Like example would be Z. Yeah, so example would be F is equal to Z times Z star. And this example, I will do it here. So the quiz is that realize that analytic functions are independent of Z star. That's one simple thing you realize very quickly. If that was the case, this must not be analytic, right? So example, so F is equal to Z star. That's X plus IY and X minus IY. That's equal to U is equal to X squared plus Y squared. And what is V equal to? If I multiply this, what is V? Hmm? No. Zero, right? Okay. So this is zero. So du by dy is equal to 2 times y. dv by dx is equal to 0. dv by dy is equal to 0. This cannot be true unless x and y is 0. So this is analytic only at one point, and that is when x is equal to 0. At that point, this is well defined. But then that's one point. This is remember a necessary condition, but not sufficient. So even at that point, you have to investigate more. So this does not satisfy Cauchy-Riemann condition. So it surely doesn't satisfy. It is not or satisfy the conditions for being an analytic function. So again, the summary is on a real function, most of the real function that we can think of has a derivative. In complex functions, not every function has a derivative. Only those functions that satisfy these conditions have a derivative. Those functions are called analytic functions. And one of the goals should be in your life, it is very hard for you to visualize it. This is very hard to visualize. These are algebraic conditions you can check all the time. But if I give you a function, you should be able to imagine that function and you say, oh, this probably is not analytic. So that's one practice you have to build, that you should be able to decipher just by looking at a function, does it satisfy this or not? And we will find simple ways of doing that, or at least to a certain extent. I won't say that this is a hard problem as to visualizing that, but that's what you should aim for, at least in the homework and other places. Okay, that's all. Thank you. Bye, Dhananjay.
Thank you. Thank you, Dr. Sajas. Bye.
Thank you.